The proposed research presents a novel approach to propagate parameter uncertainty in power system nonlinear dynamic simulations using the Koopman operator. This method captures full nonlinear dynamics without requiring derivative evaluations, retains physical interpretability, and allows for efficient evaluation of a large set of parameters with high accuracy. The Koopman operator is a linear, infinitedimensional operator that acts on observables, enabling the linear evolution of these observables over time. In this study, the technique is applied to the New England test system, demonstrating its excellent performance in terms of accuracy and computational efficiency. The method offers an alternative to existing analytical and statistical methods, which often compromise between accuracy, computational efficiency, and physical interpretability. The Koopman operator-based approach has several advantages over traditional methods. It can handle complex systems with multiple parameters and nonlinearities, providing detailed insights into the system's behavior under different conditions. Additionally, it does not require extensive computational resources, making it suitable for real-time simulations and large-scale systems. This research contributes significantly to the field of power systems engineering by providing a more accurate and efficient way to simulate and analyze power systems. The proposed method could potentially revolutionize the way we understand and manage power systems, enabling better decision-making and optimization strategies. This research paper introduces a novel method for uncertainty quantification in power systems using the Koopman operator, a mathematical tool used to analyze complex dynamical systems. Focusing on the dynamic model of synchronous generators, the paper considers both system states and model parameters as variables in an augmented model. This allows for the propagation of parameter uncertainties through the system, using the Koopman operator framework. The proposed method begins with a deterministic power system model, which is then augmented with differential equations representing the uncertain parameters. The augmented model is simulated using the extended dynamic mode decomposition (EDMD) method to estimate a subset of the Koopman tuples. These tuples are essential in constructing a Koopman operator-based surrogate model that can mimic the system's performance. The surrogate model enables efficient uncertainty quantification at a large number of parameter values. To achieve this, each parameter sample is assigned as initial conditions to the associated pseudo-states, while keeping the initial conditions of the true system states unchanged. This process reflects the randomness in the Koopman eigenfunctions, which are then used to quantify the uncertainties in the system states at any given time. The proposed method offers a more efficient alternative to traditional Monte Carlo simulations, which can be computationally costly for real-time applications in sizable electric power networks. The use of the Latin hypercube sampling technique ensures that the training dataset is well designed and efficient. The paper also discusses the computation of the Moore-Penrose pseudo-inverse of a data matrix, a crucial step in identifying a Koopman operator-based surrogate model. However, this computation might be time-consuming depending on the matrix dimension and numerical implementation. The paper concludes by highlighting the potential of the proposed method for real-time uncertainty quantification in power systems, offering a promising tool for researchers and practitioners in the field of power engineering. This section of the research paper presents the simulation results obtained using the proposed Koopman surrogate method for propagating uncertainties in power system dynamic simulations. The method is tested on a 10-machine, 39-bus New England power system with a classic generator model, where the system dynamics are triggered by opening line 1516. The parameter values of the inertia for each generator are assumed to follow a Gaussian distribution with a mean value given by the original manufacturer data and a standard deviation of 10% to account for parameter uncertainties. The authors use an MC simulation with 10,000 samples to obtain benchmark results for comparison. For the Koopman method, they set NT equals 75 and select the rotor angle of generator 2 with respect to generator 10 as the quantity of interest. Two test cases are demonstrated, each using different observables. One case uses second-order multivariate Hermite polynomials, while the other case introduces a cosine function and a sine function for each true state variable separately. The evolution of the means and standard deviations of the rotor angle difference between generators 2 and 10 are depicted in Figure 1. The results show that the means are quite accurate under both observable sets, although small differences in variance are observed during the first 5 seconds, which increase as time evolves due to error accumulation. The computing time for the Koopman operator method is recorded to be 32 seconds, similar to the polynomial chaos expansion (PCE) method based on the sparse grid rule, which also takes 32 seconds. However, the Koopman surrogate approach has the potential to better handle power system uncertainties and can serve as an alternative to the PCE method in uncertainty quantification. Figure 2 illustrates the probability density function of the rotor angle difference at t equals 2 seconds, demonstrating that the Koopman surrogate accurately represents the full probability density of the system state at a given time. In comparison with the MC simulations, which require nearly 0.5 hours to complete, the Koopman surrogate using Hermite polynomials takes only 0.5 minutes, achieving a speedup of more than 50 times while maintaining good accuracy. This section also highlights the flexibility of using different observables in the Koopman approximation, suggesting that further tuning of the observable functions could improve the method's performance in long-term dynamic simulations and commuting efficiency for larger dimensional systems. In addition, the authors demonstrate the proposed method's capability to handle non-Gaussian uncertainties. By assuming the parameter values of the inertia for each generator follow a uniform probability distribution with 10% errors, the Koopman method is shown to work well in approximating the mean and variance under an uniform distribution, as depicted in Figure 3. However, the method does not provide accurate results for higher moments such as skewness and kurtosis, indicating that improving the performance of the Koopman method in higher-order moments is an area for future research. The conclusion section summarizes the findings, stating that the proposed Koopman surrogate method achieves good performance in terms of accuracy and computational efficiency in propagating uncertainties in power system dynamic simulations. This research paper explores the application of the Koopman operator-based method in power system dynamic simulations, emphasizing the importance of understanding and quantifying uncertainty to enhance the accuracy and reliability of results. The authors conduct a comparative analysis between the Koopman operator-based method and traditional Monte Carlo (MC) simulation techniques. The paper first discusses the limitations of current methods for propagating uncertainty in power system day models, such as sensitivity analysis, approximation techniques, and polynomial chaos expansions. It then introduces the Koopman operator-based method as an alternative approach that can efficiently handle both linear and nonlinear systems with minimal computational effort. The authors demonstrate the effectiveness of the Koopman operator-based method through a series of numerical experiments. They compare the mean, standard deviation, skewness, and kurtosis of the output variables obtained using the Koopman operator-based method and MC simulation under a uniform distribution. The results show that the Koopman operator-based method accurately captures the statistical properties of the output variables, with a high degree of agreement between the two methods. The paper also discusses the potential applications of the Koopman operator-based method in various fields beyond power systems, including traffic flow and fluid dynamics. It cites several studies that have successfully applied the Koopman operator-based method to analyze complex systems and make predictions about their behavior. In conclusion, the paper presents a novel approach for propagating uncertainty in power system dynamic simulations using the Koopman operator-based method. This method offers a promising alternative to traditional MC simulation techniques, providing accurate statistical properties of output variables with reduced computational effort. The paper's findings contribute to the ongoing research in this area and highlight the potential for broader applications of the Koopman operator-based method in different domains.